So today I want to talk about, not exactly about Bitcoin, but applying Bitcoin principles to API security. And for the last 2 weeks, I've been researching this pretty deeply and been working on actual code because it boggles my mind that this is not how APIs are secured generally. And it's like, why? Okay, so I was trying to get at the bottom of why, and I'll talk about that at the end. But I want to kind of give you guys an overview of how API security is typically done, how we can improve it, and what the goals are, and that kind of thing. And there will be meetings. All right, so a little bit first about Swan, which is my startup. I am the CTO and co-founder of Swan. Swan started as a dollar cost averaging app. We basically help people save into Bitcoin on a recurring basis. And then over time, we expanded into lots of different categories as our customers kind of demanded it. Started serving high net worth people, people looking for long-term savings through trusts and IRAs, and people looking to stack for their corporations, family businesses. We're launching an app that does all kinds of education stuff, coupled with Bitcoin buying. So you're kind of, having that whole Bitcoiner journey of learning, buying, taking self-custody, all that stuff. And we're also serving employers now with our benefit plan. So those are just some of the little projects we've got going on. We're about 60 people now, and growing. And the reason that I'm kind of talking about this today is we're building an API platform, which we call Powered by Swan, and that allows other companies, other projects to basically integrate Swan functionality into their projects. One example is what we did with Spectre. So Spectre, for those of you who don't know, is a multi-sig wallet, and essentially they can make a connection to Swan, authorize the user to connect their wallets to Swan, and then they're actually uploading batches of addresses to us. We don't store the XPub for privacy reasons, so they upload a batch of addresses to us, and then they internally label those UTXOs going to those addresses, so it's a little bit nicer for you to manage on the wallet side. So that's just one of the things that you can build with Swan. And so far today, we've been working primarily with wallets. So we have Spectre, we have Ecdsa, and there's actually a Trezor integration coming soon as well. But as part of developing all of these integrations, we started really thinking about how APIs should be secured, right? Because this is Bitcoin, and we have financial transactions, and we don't want things to happen that are outside of the user's control. So there's actually 2 different authentication mechanisms at Swan. And we're not going to talk about the one that the wallets use. That one's called Ecdsa, and that one's basically where clients are authorizing Swan to connect to their wallet. So it's kind of one of those login with type of experiences that you might see in Facebook, Twitter. In this case, they just use Swan as a login mechanism. So they say login with Swan, they're redirected to our website, and then there's a handshake that happens between the wallet and our servers that allows the wallet to acquire a token for that user. That is not what we're going to talk about today. That's kind of standard. I think most people have experienced building some type of client-facing authentication. The type of keys that we're talking about today are going to be about automating your own account, which is a very common use case. You see it all over the place, whether you want to use your own Twitter account to post stuff, or you want to use GitHub to automate some kind of action. These are very common API experiences, and they usually require some type of token. So we're going to talk about API keys and how they're typically done. So, and by the way, if you have a question, you can interrupt. So the typical thing that you see out there is HTTP basic auth. Essentially, this is the client being your app here. They're sending a username and password. Sometimes that looks like a client ID and some other type of token. It doesn't really matter what you call them, but basically they're sending some type of credential. And then the server says, has a hash version of that credential and says, yep, that's the right credential. Sounds good. Very good. So here's an example from Stripe, a very popular financial app, and it uses exactly this method. You can see that in the curl over there, basically they're passing in a username and there's a password that got cut off there. But the idea is username and password are passed, the server can authorize you, everything's cool. The next kind of version that you see is basically the same idea except for using a different header. So HTTP basic auth is a well-defined HTTP spec. So there's a spec that says, when the server sees an authorization header that says HTTP basic, it has certain properties like it shouldn't be cached and all this other stuff. Sometimes people ignore that spec and make up their own header for a variety of reasons, but here's an example of that. Same idea, you're passing in some type of credential over the in the connection, And an example is voltage. I'm not picking on the voltage guys, by the way. I love voltage. We're actually a voltage customer, but that's what they use. So you have a header, X voltage auth. You get a token that they provide for you, and you stick that in your header. You make your request, and that's how you authenticate yourself to the API. Right. So those two things are basically the same, right? HTTP basic auth and special header. There's no real difference. It's just one of them is an HTTP spec thing, and one of them is basically, roll your own. There is a problem with API keys, right? One of the problems is that you leak them. You put them in your code base by accident, or you commit them into your GitHub repo, or you store them in an environment poorly. And this is an article that I found that says that over 100,000 GitHub repositories contain secrets, and there's like thousands being leaked every day, right? That's a big oops. Here's an example from Twitter. You want to go and create your app, and they give you an API key. They give you something called a secret. They give you even a token you can use right away. That's a big oops, right? Because what did I just do? I just shared the screenshot. If anybody takes a screenshot of this, they can use my Twitter app. So that's a big oops. Of course, all of these guys are always saying, hey, hide it, don't show it to anybody. This is only shown to you one time. Doesn't matter, because you've already shown it, right? The other thing you kind of see is some type of token exchange mechanism. This happens when you send some kind of username or password or some type of API token, and the server hands you back a different kind of token. That's called a bearer token. And there are, again, HTTP standards around this. There's an RFC around this. This is called a bearer token. You submit it back to the server, and it's basically the same as we've seen before, except for now the server has some control over that token, so it can revoke it. It can, it can verify additional things around it. And here's an example from Salesforce, the #1 SaaS product in the world. And you can see, in order to get a Salesforce token, you need to pass in 4 different pieces of data. So you've got your client ID, secret, username, and password, but there's still plain text things that you got from Salesforce at some point. So it doesn't matter how many different bits of data you stick in there. At the end of the day, it's still the same problem. But the nice thing about this token exchange, at least you can revoke these tokens. So the server can actually say, that token is no longer valid because I issued it. I can put a timestamp on it. I can put various guards around it, things like that. So it's nice, but you still have secrets. The other thing that you see, this is probably the most advanced type of API auth mechanism, which is signed requests. So this is used by AWS. AWS was not happy with any of the existing token authentication mechanisms that were out there, so they invented their own, of course. They call it API SIG v4 or something at this point. And the idea is they give you a client ID and secret, but you don't submit those back to them. You do submit the client ID, but the secret is actually not used. It's not given back to them. It's used to sign the request. So now we're getting closer to what I think is a bit more quick Bitcoin-y. You're signing. You're proving that you have the secret, and you're taking the string, which is basically your request. You're putting in all kinds of signature stuff, following their algorithm, which is very, very advanced and has lots of protections for various types of hacks. Looks super secure, but where did you get those keys? Where did the secret key and client ID come from, right? Well, it came from their console. If you guys have ever used AWS or any other cloud, they pretty much all work the same way. You say generate credentials, they give you the credentials, they let you see them. It's one time, so at least AWS does a good job there because they never will reveal it to you a second time. You get to see them once. You can download them in a file, you can reveal them in the console, and they tell you, warning, do not share these with anybody, right? Except where you just download them to your laptop. So you just shared them with somebody. And now you have a problem. What do you do with all these secrets? They're everywhere. They're on your laptop. You've shared them with somebody by accident. You've shared a screenshot. You've put them into your repo. Maybe you have malware running, so when you were copying it, now it's in memory and it's been leaked. Maybe you are a developer and you forgot to delete it on your laptop, and then that laptop was stolen and somebody was able to get the secret. Maybe you accidentally put it in your GitHub repo. Maybe you did everything right and you actually put it in your environment, you're running app, but you didn't secure the environment properly and somebody got in that way. Or maybe you really did a great job and you secured everything except for there's the admin who controls the secret store. So let's say you're using like AWS Secrets Manager, you're stuck in your secret there, but you still have an admin who's able to access the secret. and now that admin gets hacked, and now your secret is leaked. Secrets are impossible to protect. Okay, that's the bottom line. Whenever you have a secret, you cannot protect. What if I told you we can do better, right? The whole idea here is we're going to use Bitcoin's concept of public-private key encryption. Now, I did not invent anything. This idea is extremely old, right? Public-private key encryption is very old. Even use in APIs has actually been around for a long, long time, but it doesn't seem to be popular. And that is a huge problem, and I hope that the one takeaway today, after I show you guys how this is implemented and how this works, is that you all go home to whatever other companies you interact with and you demand that they implement this kind of API security. Because it's absolutely embarrassing that in 2022, we are still guessing around secrets. So how does this idea work? Basically, it's kind of like that AWS idea, but instead of using a secret key, you have an actual private key. It could be an RSA key, it could be an Ecdsa key, which is how Bitcoin signatures work. And you sign a token for every request you want to the server. And one of the big benefits here is that every request you make has a unique signature. So it's just like Bitcoin transactions. Just because you signed a Bitcoin transaction does not mean you revealed your private key, right? And all these other examples, if we kind of go back to something like this, if somebody malicious was in the middle of this request and saw your username and password, or somebody malicious got onto your laptop and saw your secret, they can now produce additional requests to that server. You would never know, and you would be compromised. Now, you could know through logging, you could know through alerting, but these are ways to try to salvage a bad situation. The bad situations already happen as soon as they have your credentials, right? So what we're going to go towards is we're not going to send credentials over the wire. We're going to have a private key and a public key. We're going to sign a token with a private key, and our server is going to look up the public key that has been pre-registered, and they're going to verify the token. All right, so let's look at how this works in practice. This is the OpenSSL command line, which you can get pretty much in any platform. This is for Mac OS, but probably works the same on Linux. I don't know. Yeah, it's been a while. Yeah, there you go. So this is an example generating a RSA key, which is at this point not best practices. It's a little bit weak. I mean, 4K is fine, but still potentially not great. The better way to do it is Ecdsa, which is actually how Bitcoin works. And this command here generates a private key using the SECP 256K1 curve, which is actually Bitcoin's curve. And the cool thing is, and we'll get to this in a second, is that it's actually supported by some cloud hardware stuff like KMS and Amazon. So you can basically create signed requests, and I'll show you guys how to do that. So we're going to generate these keys, and this is how our API works. And we've been scrambling the last 2 weeks to actually build this to prove that this is a thing, and it works. You go to our dev portal, you put in a name for your app, and you paste in the key that you got from this key generation process. This is a public key. That means it's totally shareable. There's nothing leaked here. I can show this guy this screenshot of my production credentials, and I'm totally not scared. It's a public key, right? Once you save the public key, you get an app ID. This is also not secret. This is just an identifier telling us like who you claim to be. The way we're going to verify who you claim to be is your private key. So this identifier by itself, if it leaks, no big deal, because it's literally just an ID of an application. And this is actually a working code example. If anybody's interested, there's a Swan buyer project under the Swan Bitcoin GitHub organization. And it actually will walk you through generating these private keys, uploading the public key, and then signing the request. We're actually going to look at the code that does that, so you don't have to go there right now. But just so you guys know, the code is up there. And yeah, show me the code. Let's go. So this is very, very easy. This is the entire code, okay? So this is the client, and let's just walk through. Yeah. So bit by bit, what we're doing, we're using the Jwt library. So this is standard stuff. Jwt is essentially a token that contains a set of claims. These claims are essentially key value pairs. Some of them have special meanings, some of them don't. All the ones we're using here have special meanings. So they have something in the JWT spec that they mean, and we've actually commented them here so you can clearly understand that. The first thing is the issuer claim. So this is me saying, hey, I am signing on behalf of myself. I am the issuer. My ID is blah, and that ID is basically what we're having our server generate here. Just a unique ID. It doesn't have to be anything special. Just a UUID. So here in the client, we're saying the issuer is that unique ID. The subclaim is the subject. It's also this is something that's used when the subject of who's trying to do an action is different from whoever issued the token. But in this case, we are the issuer and we are the subject, meaning I'm trying to automate actions on my own account. So I'm the issuer. I'm also the subject. The odd claim is audience. So this is telling the server who this token is intended for. This is just to prevent servers from like taking that signature and token and sending it to some other server that's, and that server would then consume that token. So servers are supposed to enforce this audience claim. And then there's scopes, which is basically like, what are you trying to do? So example would be, I want to make buys. I want to list my payment methods. Those are some of the scopes that Swan provides, but your server can provide a set of resources and a set of scopes. This is all totally up to you how you find that. And then there's a thing called JTI, which is a unique ID. And this is, we're just generating a unique ID for every request. That way, if somebody intercepts that signature, they cannot reuse it, because our server is actually going to enforce that that unique ID is only valid for a certain period of time. And during that period of time, if we see it twice, we're going to reject it. And we'll look at how the server actually does that. But that's the idea. So we're creating a payload, which is saying, here's who I am, here's who my token is for, here's what I want to do, and here's a unique ID to prevent replay. We then are going to read a private key. Now, I'm going to get into how to actually secure this, because remember we talked about you never want secrets anywhere. This is not production code, but for the purposes of this demonstration, we have a private key that we generated on our file system. We're going to read it into a file. We're then going to call the Jwt library to sign that token with that private key, and then we're going to post it to the server using the bearer token mechanism. Okay, so again, what we've done is we've claimed a bunch of stuff. We've used a private key to sign those claims, to prove to the server that those claims are true. And now the server has to validate those claims. Any questions on this part? Because this is probably the hairiest part of this.
This looks a lot like OpenID Connect.
Yes.
Are you talking about doing expiration dates and refresh tokens?
Exactly. So this technically OpenID Connect or IDC has this idea in it. It's called Jwt Private Key. I can't find really any good examples of like production APIs implementing it, which is very strange. So I'm explaining the fundamental concepts, but you're right. This basically is part of the the OpenID Connect spec. And the next step, we just haven't gotten to it. The next step is to see if we can get an off-the-shelf OIDC library in Node to do this for us without having to implement it. But the implementation is trivial, so I will show you the implementation. But yes, it would be better if we just followed the OIDC spec. But basically, this is damn near close to the OIDC spec. All right, so, and by the way, it seems like everybody invents their own API out anyway, so all these specs are great, but like, as you see, AWS, like, Twitter, they all have their own auth schemes. This is what the server looks like. Again, extremely small amount of code. And what are we doing here? So we're taking that token that was given to us by the client, we're splitting it out. We're using the Jwt library to decode it. Now, decoding is not verification. Decoding is just telling you what's in the token. So I see all of this stuff that has to be the issuer, the unique token, when it's supposed to be expiring, all that kind of stuff. And then I'm going to find the certificate that was registered with me in my database, right? So if we go back again, remember this stuff over here. When you submit your public key to Swan, we literally just put it into a database and we map it to this app ID. So somewhere in our database, we have an app ID and a public cert. Very simple. Again, it's public certs. We don't have to worry about securing them. Great. So the database is now going to find that cert using that issuer ID. We can't find it. Oops, you can't talk to us. You're not authorized, right? If we do find it, we do additional stuff. One of the things we do is replay protection. These 3 lines of code here, they basically implement replay protection. It's not production code. It has not been audited, but it basically implements replay protection. What it does is it stores that JTI in Redis for the expiration period. So let's say you have a token that's valid for 5 seconds. We're going to put it in Redis for 5 seconds. After those 5 seconds, it's simply going to be invalid because it expired. During those 5 seconds, it's going to be invalid if you send it to us twice because it's in Redis. Really important if you do implement this, they use some type of Redis locking library that's designed for distributed locks, especially if you have a real production system. But that's the idea. We're just going to verify that it hasn't been replayed. And then the final step here is actually using the Jwt library itself to verify the signature. So here we are literally just saying, is this token actually signed with the private key that it claims to be signed with based on this public key? Okay, so this is the entire server implementation. And like Nick here pointed out, Nick?
Yeah.
That OIDC, you could probably get an OIDC off the shelf library to do this for you. But that is to come. All right, so far we've implemented a system that uses public-private key encryption that allows us to submit an identity claim. I am Jan, I'm this application. The server can then verify my identity using the public key. And the server did not produce my secret. That's the important thing here, right? The server, it's not like in those other examples where the server gave you a token. The server did not produce a secret. I produced a secret. It's on my laptop so far. So pretty good. Better, of course, than copy and pasting it because things can go wrong there. But still a problem. So now we want to take this to the next level. If you don't store the secret, you can't leak it, right? So that's our key finding here. So now we can think about how do we secure private keys? If I have to generate it on my laptop, I'm back to the same problem. Somebody could hack my laptop, the keys lying around, it's a big problem. Well, it turns out there's a thing called, yes, sir.
Look up upkeep by ISS on the right side.
Yes.
What is ISS?
Okay, so yeah, let's go back to this example. Thank you. ISS is the issuer of the token. So the issuer in this case is like your app ID, basically, right? It could be like you tend to want to have these be unique, but it could just be like my name, like Jan, let's say, right? App ID is Jan. I'm saying the issuer is Jan, and I'm using Jan's private key to sign this claim. And then this is then using that issuer to find the public key that I registered. Does that make sense? Any other questions? Sorry, I know I'm going pretty fast. Okay, cool. So, so yeah, the idea here is it turns out there is a mechanism for not having to generate private keys on your laptop. It's called an HSM. Okay, it's a hardware security module. So these are, you guys know cold cards. Cold cards basically an HSM. It's a hardware security module. It generates keys in secure enclave. You can never get the key out of the device. You can't yank it out by force, nothing. It's in there, right? Now, I'm going to show an example using Amazon. They have something called Cloud HSM. So they have hardware running in their cloud, and you can invoke this hardware to generate private keys that you will never have access to, but the hardware can then sign requests. So this is huge because that means that if you've never seen the private key, you can't leak it. That private key is generated inside of a piece of hardware. So what we're going to do is instead of this idea here where we are reading the private key from the file system, we're going to call some kind of HSM. In this case, it's going to be Amazon KMS, which is Amazon's key management service. It's going to sign requests for us. And the way this looks is, this is the UI, but there's also a command line for this as well. Go to Amazon, you create a key, you say I want an asymmetric key. Asymmetric means public-private key encryption. Key usage is sign and verify, because that's what we're going to be doing with it. And here the key spec we're using is this one, ECC, SecG, whatever. What that means is I want to use Bitcoin's signing mechanism. We don't have to use Bitcoin signing mechanism, but why the hell not? This is a Bitcoin conference, right? We like Bitcoin. That will produce a private key inside of Amazon that you will never have access to, no matter how hard you try. It's inside of their hardware module. What they will give you is a public key. You will then take that public key, again, paste it into the API that supports public key verification, such as Swans. And then there's a little bit more code, but this is the gist of it. You're going to call Amazon's KMS service. You're going to tell it to use the Ecdsa algorithm to sign, and you're going to give it a payload, which is that same exact token stuff, and it's going to give you back a signature. And now they are doing the signing inside of their secure hardware. You've never seen the private key. You can't leak. There's no secrets to protect. You're in good shape. So that's what we built. We built this in 2 weeks. And I think the reality, the meat of the code, most of it was research and understanding how this works. The meat of the code is like 100 lines of code. It's very, very easy. So the question is like, why isn't everybody doing this, right? why aren't all APIs out there secured by public private key encryption? And I honestly can't give you a good answer. I looked at all the APIs from major tech companies. The only one I found that was loudly advertising this was Twilio. Twilio Enterprise, in fact, Twilio's normal API auth doesn't do this, but Twilio's Enterprise Edition does have this, and they call it public key client validation is what they call it. If you Google that term, nobody else has that term. So they invented it. There's no industry standard for it. There is something in OIDC, standard, which is a token exchange standard and an identity standard. There is something called Jwt Private Key, which I've literally discovered in the last week of researching this, and I'm still, this presentation was happening while I was doing this research. I'm still not confident in understanding why this is not widely implemented. Because every article you read about JWTs and signatures and all this, they all tell you to use, first of all, Ecdsa, because it is the best security standard we have for signing, and the keys are small, the signatures are very strong. So they all tell you to do that, but then nobody tells you to implement your API to validate your clients by public keys. And the main reason I think this is probably not happening is just momentum. It's just because people got used to cutting and pasting tokens. They've been doing it for 20 years, and they're continuing to do it. And whenever you start to build a new project, you look at other projects that are out there, you look at the main tech companies that are doing APIs, and you copy what they've done. You basically implement the same thing. And I want that to change. I want us all to be building APIs that are public key verified, especially when it comes down to building APIs that control Bitcoin. I mean, something like Voltage, again, where customers love Voltage, but Voltage controls Bitcoin, right? I don't want that to be a token that could leak. I want that to be a public key that they store and a private key that I have in my cloud HSM that never leaves a secure enclave. So we're trying to actually build some type of industry coalition. I'm trying to figure out how to make this happen, how to make this popular. I think it starts in the Bitcoin industry because we understand public private keys better than anybody, but we need to spread it outward to every company, and we need this to be like a standard because it's absolutely crazy that it's not. So yeah, if you guys go to developers.swanbitcoin.com, there is some information on how to build things with Swan. Since this is a demo, the only API we have exposed so far is the Smash Buying API, which means you can make market buys, which is great. We all should be buying on a regular basis. Some of the things you might want to build with that: physical Smash button, Alexa integrations. You can link it up to tweets, things like that. Smash from your browser extension, and we're very close to releasing a Lightning Send capability as well. And once we have that, that'll also be part of this API where you can actually then, let's say, pay for a paywall using your Swan account, or activate some other API that is Lightning powered, which is another cool authentication mechanism that we're not going to get into today. But that's what I'd love to see. Yes.
I mean, you just brought it up, but I was going to ask LNURL auth.
Yes, exactly.
This idea, right?
It's this idea.
Okay.
Yeah, so I'm not an expert in LNURL auth. I know at very high level, but I think it's a similar idea.
Yeah. And then are you following BIP 322, which is trying to standardize the actual signature, and then just changing up a couple things? Because like, if you make a signature in Electrum, like it might not work in another wallet because there's no standard. They're non-standard.
Okay. Yeah, this appears to be whatever I've done here so far seems to be standard. Like what KMS does is standard. What the JWT library does is standard.
Yeah.
They all use the ES256, which is like a standard.
Yeah, that is. But like the stuff in Bitcoin, like if you make signatures, it's like only your wallet. You can only bet that your wallet will be able to read that.
Okay, I see. Yeah, that's definitely something that needs to be standardized as well, for sure. Yeah, back there.
So like this is all good for like kind of like B2B like developers like implementing this stuff. But, like, have you guys done any research on like say like the user logging in the Swan has like email password, and like generally use just like a bearer token there. So do you guys do something like, have you figured out a similar way where you like?
So we don't use passwords. First of all, we use passwordless auth. So we email you a link, and part of the reason is credential stuffing, where people just cycle all your passwords from other sites. But right now, when you exchange your email magic link, you get a token back. The token we're using now is actually HS256, which is a symmetrically signed token. We're going to move to this auth scheme as well, which at least the server will sign an asymmetric token, so that's better. But yeah, I mean, it should be done everywhere, right? It should be done everywhere. And if you look at something like Auth0, which is that's probably the most popular provider of these kinds of services, all of their articles are like, yes, sign all your tokens asymmetrically, but they're almost always from the perspective of the server. Like, like your login example, right? Where somebody logs into a system and the server gives them back an asymmetric token. What we're saying here is the client is the one producing the token because they're testing their identity, right? Yeah. So they just need to register their public key with the server. And actually, this is now a very popular concept called zero trust architecture. So when you're building services in general, like say you have two services inside of your cloud or whatever, and they're communicating. Well, they should not trust each other just because they're on the same VPN or something. They should actually send tokens to each other that are asymmetric, right? So one of them has a public key, the other one has a private key. And if you look at how some of this is done wrong, is you will have symmetric keys everywhere in these organizations, and actually you can have two different services running in your corporate environment, and one of them, both of them have the same key because they have to verify each other's tokens, which means that one server can steal another server's token or produce tokens to sort of impersonate the other server. So now you have a problem within even a corporate architecture. So you want to move to a situation where every single transaction is validated with public-private key. It doesn't matter if it's inside your firewall or between you and a client you don't trust, but it's all got to be this way. Yeah.
So I have a cold card, and I'm very familiar with the whole HSM concept, and I use it in an air-gapped manner. But can you talk a little more about this cloud HSM? I'm not too familiar with that. Like, it sounds like another layer of abstraction to me that doesn't exactly solve the problem, because you can still have similar problems up at that level, right? Up at the so what links the cloud?
So the cloud is just because most modern apps are running, if they're not running on your Umbrella node or whatever. I mean, I think in the future we're all running our apps completely locally.
Right.
But there are still many types of server-side apps that will exist probably in perpetuity, right? And in those environments, you are in some type of cloud environment. Now, the cloud HSM is really just an Amazon, like it's a cloud abstraction over this idea. They have hardware, and they give you an API call to cause that hardware to do something, right? To sign a transaction. So you do have a problem a little bit there in the sense that like somebody could, for example, hack that part of the connection, right? But in our case, what we're doing is like it's actually the client, right? So if you're a Swan client app, and you're just developing your own little Smash Buy app, you can have your own cloud instance and you have your own key. And the only thing that could possibly be hacked is like that connection causing you to sign requests that you didn't want to sign. Right. It's not like a compromise of your server, it's a compromise of the end client. But you can't get away from that if you run something in the cloud. It's going to be in the cloud.
I mean, they have admins too, so it feels like maybe the admin thing, like I'm sure they have.
Well, Amazon is running those services on actual HSM.
Exactly.
Right.
So it's like a big hole.
Right.
Yeah. So even their admins can't get the private key, but they could probably cause it to sign transactions. So
Right,
it's
that's what I'm worried about.
Yeah, they can get your Amazon API.
Okay, cool.
One more thing that is still problematic about this is the initial registration. Like, you still need to make sure that whoever gives you the pub key is who they say they are.
That's true, but I mean, this is where you're just getting it through traditional auth. Like you have to log in to the site in order to do this, right?
Yeah.
So at some point, somebody's got to like log into something.
Yeah.
We were thinking like, is there a way to do this without having somebody do the login? But essentially, you have to give them a token. Like you can give them a token that they can curl into it. It's the same fundamental problem. I feel like email-based login plus 2FA is really, really strong. And then on top of that, you can basically upload your public key.
And then also key rotation. In case
Yeah,
there's an issue.
like key rotation is a great point. It's actually very easy with this because you could just upload a new public key, right? Or you can delete an existing connection that exists, and all of a sudden nobody else can issue these tokens. The one thing that is sort of problematic is that in this scheme, the client is producing the tokens. The server, there's no token exchange, which means that if a token is bad, we can't revoke it. You can introduce token exchange, so you can have client produces a token claiming who they are, you verify it, and you give them back a server-side token, and then they can use that. But what we're recommending instead is that these tokens are just extremely short expiry and have these JTI replay protections. That way, that token is literally only valid for that one request. So like, there's not really a need to revoke the token because it's only really valid for one request. Yes.
Yeah, I'm not sure if it's a question or the comment. But we didn't really get ourselves out of the Bitcoin, and we easily talk about public keys and private keys, but purely just API perspective. People have got something up there, they want people to come and use it, but you want to authenticate it, make sure you're properly authorized. And you ask the question like, why aren't they using it? And then I think actually, have you actually asked some of those large companies who's using API, the standard way of doing it, click this, here's a key, cut and paste this? is government or that's my question. Have you ever like to ask them?
No,
like,
we're
what
just in
is
the
it?
early phases of
Yeah.
this. So we actually formed a coalition with a bunch of Bitcoin companies, and I'm going to start inviting other people to it. And I started circulating this to 6 or 7 companies. Nobody said that it's insane. I validated this with a number of security experts. Nobody said that it's insane, and nobody can really explain why it's not
Or
common.
maybe that's how you're doing it in your company, right?
Yes.
One is backing up, backing up PHP keys. There's no good way to do it without being really good at computers.
Right.
So that's an
Yeah,
issue. And
unless you have
then,
this HSM thing, but yeah.
and then it's free to make them. So there's no incentive to hold on to it and make sure that it's like
Right.
yours forever. So my opinion is if we can tie this somehow to people's money, there's some incentive to like
Yeah.
make sure you hang on to it. And then also with the mnemonic backups, that's like much easier to back up in like, you know, like a sane way.
Yeah, that's my common portion of it. I mean, we've been doing it,
Yeah,
and then
right.
it kind of works, right? Risk management, okay, it kind of works, you know, it's not as safe, but it's been doing so far, good so far. The second thing is, as I said, most people have no idea. We're just talking about private keys, and public keys, and you got to do generating, parity, and going on. You probably know the
That's
users,
true,
right?
but
They don't want to do that. Just click on this, cut and paste it, you're done, right?
I think that's true, but it's kind of lazy because like most developers don't understand what they're doing. Let's not say most developers. Many developers don't understand what they're doing even better, right? Like, I've worked in the industry for 20 years. Many developers don't actually understand HTTP, APIs, nothing. They just cut and paste code. So like, what's the difference to them if the end result is that they cut and paste, you know, this code, wherever this is, I can't find it.
You can also put it in a library, right?
Exactly, yeah, it is in the library. This code here, and you can make it even simpler, but this code is, I mean, 10 lines of code. And it's just, half of this code is making an HTTP request, which they're gonna do anyway. And the other half of it is just this is the bit up here that's actually producing the token. And like, is that really that different from most code examples that you find? I mean, you have to generate the keys. That's the only additional step. So yeah, maybe that's the friction point, I don't know. But it just seems, like the trade-off is so asymmetric. Not to pun on this too much, but you know, this way you have complete security, or well, not completely. There's no such thing as 100% security, but it's damn near close. Versus, you know, tokens that are leaking all over the place, and like I said, 100,000 tokens that you can GitHub. So.
Yeah, but on the other hand, for a normal user perspective, it's like you kind of trust the institution that you deal with, whether it's banks or whatever. This is what you do, we do it, and you know, hopefully everything's good,
Right.
even though it's not. Where here now you say, oh, actually you are the one who owns this private key. You gotta figure out maybe even to an HSM, whatever. No, just give me something there, tell me what to do. I just kind of do it. I think that's a definitely psychological thing that you know, obviously we're not talking about programmers. I'm talking about users who are like, you want me to do what? What am I doing to use?
But look,
so,
I mean, when people use standard APIs, they still have to figure out how to secure the secret. So what are they going to do? Well, they're either going to stick it in GitHub, which is totally wrong, or they're going to actually have to use something like a secrets manager tool of some type, right? So even if they don't use an HSM, they can stick the private key in the same secrets manager, and it's no different than what they would have
it sounds
done.
fantastic.
But it's just way better. But HSM, of course, upgrades this whole thing. But yeah, I mean, it is more friction. I mean, I'm not gonna lie, it's more friction than your typical cut and paste token into this thing. But I would argue with financial transactions, like this should be the way. Like Stripe should not be offering an API that's token based.
LNURL is very frictionless if you're already using it.
Yeah. LNURL, I mean, I would love to add that as the next layer of auth here, that's for sure, because we're just dipping our toes with Lightning, so I don't want to get out over my skis and talk about stuff I don't understand yet. But we're getting into Lightning, and that's going to be definitely an option.
Curious if you looked at Lightning Service Authentication tokens in your research. I know it's like more for paid APIs, but
Yeah. So I think that's a similar idea as the LNURL auth. Is that what we're talking about, or is there a different
I think they're somewhat different.
Well, in any case, yes. I mean, I think that's similar, and again, I don't know as much about it, but I'd like to, and I think that's going to be research as well. But the whole point here is that this also is kind of like generic. It's not really Bitcoin oriented. It's like if you're writing any API, you should do this. If you're writing one that is Lightning oriented, then for sure you should use something native Lightning authentication.
So would you say the only trade-off here is that the client has to deal with the KSM and generating the private key?
Yes. Yeah. The client has to either have a KMS or HSM type of functionality, or they can stick the key in the secrets manager like they would normally with any other, or in their environment.
Oh, so they could choose to reuse.
They could choose to keep the private key as if it was any other secret, and it isn't fundamentally different. it's still, the rest of this path is still better because, like, for example, every token you send is now unique and it's signed with its key. So it's better in that sense. Like if the token itself is intercepted, it can't be reused. Whereas if you go to like a traditional API, like, you know, like Voltage or something, or Twitter, whatever, like once you have this key, reuse it all day long, right? You can make requests, and that's a problem. So if you were somehow to man in the middle of a request, you could steal this. Whereas at least in the signed API, you man in the middle of a request, the worst thing you can do is you steal that one token, and then like you can't steal anymore because it's different on every request. But yeah, caveat, I am not a security expert. I've learned all of this in the last month or so, which was, you know, I think it's often good to approach problems with a fresh mindset versus, you know, kind of like, if you've written no IDC spec and then you're like, why isn't anybody using this? So I'm trying to figure that out.
Yeah, it's like a comment, but I did like the same thing like maybe 6 months ago. I was like, why like are like email providers for like just give like a public key to send like every single list. It's like this is not secure at all. I was like, why is no one needs like actually like sign things? And yeah, so
Right, exactly.
I echo a lot of your
So hopefully I'll give an update. I'll be probably putting out a blog on this once I get more research, get more feedback, and we are getting a third-party audit on this idea. But again, it's not a new idea, and it's part of the OIDC spec technically. So my hope is in the next couple of weeks we're going to figure out a way to get like a standard OIDC library to do this off the shelf, and then we can publish some code that says like, hey, this is not crazy. It's totally supported. It's part of the spec, and then maybe we ask the question of why nobody's doing this. Yeah.
Have you thought about like setting the request body at all?
Sorry, say again?
Signing the request body.
Yes, I've been thinking about that, and I know a lot of APIs do it, and actually Amazon does this. It's not clear to me if that's any better or not than just using this like unique token claim, because it basically makes the token unique anyway.
So I think the reason that Amazon does it and the reason to do it is because I have to trust that you're going to process my request as I intended, right? And so, you know, financial transaction, let's say an attacker adds their own bank account to my account via an API key in some way.
Right. They can tamper with the body.
Yeah, like an internal attacker adds Swan.
Yeah.
And so if I sign the request, I can prove that, you know, what they requested, like that I originally.
Yeah, I think that's probably right. There's, I have to find, I mean, there's HMAC signatures, which are kind of standard for this. I want to see if that's like what is recommended in this OIDC spec, or, because they don't seem to provide any recommendations as far as I can tell about how to do this. I mean, you can just take an HMAC of the body into the header and that will solve the problem. But yeah, I think that's probably right. Yeah.
How about the shirt?
Yeah, thank you. Anybody else? Perfect on time.
Yeah.